Hey, have you ever stopped to wonder how we get a number from the real world? How does a physical feeling like heat somehow become a digital readout on a screen? Well, today, we're going to follow that signal's journey and break down exactly how instrumentation systems make it all possible.
I mean, think about it for a second. How do our machines actually sense the world around them? From a rocket hurtling through space to the simple thermostat on your wall, they're all constantly measuring physical stuff. So, what's the secret? How do they do it?
The answer, and this is pretty cool, is that they all rely on the same fundamental thing, an instrumentation system. You can think of it like the hidden nervous system of all modern technology, and it's constantly measuring, processing, and reporting on the world.
At its heart, that's really all an instrumentation system does. It's a translator. It takes some physical parameter, like temperature or pressure or speed, and it converts it into a number we can actually use. It literally turns the physical into the digital. Okay, so let's dive in. This diagram right here, this is our roadmap for the signal's entire journey. It moves through 5 key stages. First sensing, then conversion, manipulation, transmission, and finally presentation. We're going to walk through each one of these steps to see how a raw physical input becomes genuinely useful information.
So, our journey kicks off right here at the primary sensing element. This is where the system makes its very first contact with the physical world. A great way to think about these components is as the sense organs of a machine. They're its eyes, its ears, its sense of touch.
And the key player in this first stage is something called a transducer. Its one and only job is to take something that isn't electrical, like the force of you pressing a button or the heat coming off an engine, and convert it into an electrical signal that the rest of the system can actually understand and work with.
Now, these transducers come in 2 main flavors, and it all depends on how they get their power. You've got active transducers, like a solar cell. They're totally self-sufficient. They generate their own electrical signal directly from whatever physical thing they're measuring. But then you have passive transducers. They need a little help. They require an external power source, and they work by changing that power based on what they're sensing.
All right, so we've got our initial electrical signal, but our journey is far from over. That raw signal now has to go through a whole processing phase where it gets converted, boosted, and basically prepped to be sent on its way.
And here's the problem. The raw signal that comes out of a transducer is, well, it's rarely ready for prime time. It might be an incredibly tiny voltage, way too small to be useful, or it could be a smooth analog wave in a system that only understands the black and white world of digital ones and zeros. It's just not usable, yet. This is where the signal gets a major glow-up. First, a variable conversion element might use what's called an analog-to-digital converter, or ADC, to translate that analog wave into digital ones and zeros. Next, a manipulation element, which is usually just an amplifier, boosts that teeny-tiny signal to make it stronger and clearer. And finally, the transmission element takes this nice, cleaned-up data and sends it on to its destination.
And that transmission stage, it is absolutely critical, especially when you're talking about huge distances. Just think about controlling a spacecraft. You obviously can't run a wire up there. Instead, engineers rely on a telemetry system that sends all that crucial data as radio signals across millions of miles. It's a perfect, really high-stakes example of that data transmission element in action.
And here we are. We've reached the final destination of our signal's journey. After being sensed, converted, boosted, and transmitted, it's finally time for the payoff, turning that electrical signal into something a human can actually look at, understand, and act on. This last step, the data presentation element, is really the face of the whole system. It takes that fully processed electrical signal and displays it, whether it's for monitoring or for control or for analysis. It's the essential bridge between the machine's world and our own. And you see these things literally everywhere. The little needle on a voltmeter, the numbers on a digital clock, the graph on a hospital heart monitor, or the speedometer on your car's dashboard. Yep, those are all data presentation elements, giving us that final meaningful number. But wait, there's a really crucial twist to our story. No matter how perfectly designed the system is, there's always a little ghost in the machine. See, no measurement is ever absolutely perfect. So we have to talk about error. So what is error? Well, it's simply the difference between what the instrument says the value is and what the actual true value really is. And it's so important to understand that you can work to minimize it, but you can never, ever completely get rid of it. It's just a fact of life in measurement. Errors pretty much fall into 2 main categories. Think of it like you're shooting arrows at a target. Systematic errors are like having a misaligned sight on your bow. All your arrows might be clustered really close together, but they're all consistently off to the left. It's a predictable flaw. Random errors, on the other hand, are like having an unsteady hand. Your arrows just kind of scatter unpredictably all around the center. These are caused by tiny fluctuations you just can't correct for.
So we can sort all these errors into three main buckets. You've got gross errors, which are basically just human mistakes, like misreading a dial or writing down the wrong number. Then you have those systematic errors, the ones that come from the instrument or its environment. And finally, the random errors, those unavoidable, unpredictable variations. Now, the key insight here isn't just knowing they exist, it's understanding how engineers manage them. Gross errors, you minimize those with careful procedures. Systematic errors, you can correct for those with calibration, like zeroing a scale. And for random errors, engineers take a ton of readings and use statistics to figure out the most likely true value. It's a constant battle to get closer and closer to perfect.
Okay, so we've followed the signal's journey from start to finish, and we've even confronted the reality of error. But why does any of this matter so much? Well, because these systems are the silent, invisible foundation that our entire modern world is built on.
Let's ground this whole idea with a real-world part. This number, 750 square millimeters, that's the area of a tiny quartz diaphragm inside a specific pressure transducer. It's a real part inside a real system, doing the very real work of turning physical pressure into a usable electrical signal. It's where the magic happens.
And when you zoom out, the impact is just immense. From guiding spacecraft and monitoring a patient's heartbeat with an ECG, to controlling the temperature in a massive factory or analyzing the stress on a bridge, instrumentation systems are absolutely critical. They're what make our technology safe, efficient, and reliable.
And that brings us to one last thought. This journey of a signal, from the physical world all the way to a meaningful number on a screen, is what enables our smart devices, our automated factories, and our biggest scientific discoveries. So, as our world gets even smarter and more connected, the real question is, what's the next physical thing we're going to need to measure?